Hi, I am B. Janardhan Reddy. In this video, I am going to explain Kirchhoff laws. Kirchhoff laws, which are used to analyze circuits that cannot be broken down to simple circuits by the methods of replacing equivalent resistances. In the previous videos, I showed some problems on series and parallel connection of resistors. The methods used for replacing series and parallel combination of resistors by their equivalent resistances are very useful for simplifying many combinations of resistors. However, they are not sufficient for the analysis of many simple circuits, particularly those containing more than one battery. To analyze such circuits, two laws, namely Kirchhoff laws, are used. So, in this video, I am going to explain Kirchhoff laws. Many electrical circuits cannot be reduced to simple series parallel combinations. For example, two circuits that cannot be so broken down are shown in figures below. See here, this is a circuit which contains two batteries and three resistors connected in this manner. And here is another circuit which contains three batteries and some resistors in this way. And these circuits cannot be broken down to simple series and parallel combinations by replacing their equivalent resistances. Okay. However, it is always possible to analyze such circuits by applying two rules devised by Kirchhoff in 1845 and 1846 when he was still a student. Okay, so we can analyze these two circuits by using Kirchhoff laws or Kirchhoff rules. Okay. There are two terms that we will use often in Kirchhoff laws. See here. First, here are two terms that we will use often. What are those two terms? Let us see. Junction. What is junction? A junction in a circuit is a point where three or more conductors meet. In figure A, points D and C are junctions. See in this figure. In this figure A, the points D and C are junctions. Why? Because three conductors are meeting at those points. See here, at point D, three conductors. 1, 2, 3. Three conductors are meeting. Here also 1, 2, 3. Three conductors are joining or meeting at point C. However, points A, B, E, F are not junctions. Why? Because there only two conductors are meeting. So, a junction in a circuit is a point where three or more conductors are meeting. Okay? So D and C are junctions. Similarly, here you can see one more circuit. In figure B, points B and F are junctions. This is the figure B, and let us identify the junctions in this circuit. See here. At the points B and F, three conductors are meeting. That's why B and F are junctions. and the remaining points are not junctions. Why? Because at those points only two conductors are joining. So B and F are junctions in this circuit. Okay. Another term that we will use often in Kirchhoff laws is loop. What is loop? A loop is any closed conducting path. See here in figure A, these are the loops. You can see this is figure A in which I will show you some loops. I will start at point A and return to the same point. So this is a closed conducting path. See here A, B, C, D, A is one loop. Similarly, D, C, E, F, D is another loop. Next A, B, E, F, A, the other loop. Okay. So in this circuits, there are three loops we can find. In figure B, some more loops I will show you. This is figure B in which you see here C, B, F, E, C. This is one loop. C, B, F, E, C. Next B, D, G, F, B. So these are the loops. Okay. Kirchhoff's rules consist of the following two statements. See here. Kirchhoff's two rules. The first one is Kirchhoff's junction rule and the second one is Kirchhoff's loop rule. Let us study one by one clearly. Let us study the Kirchhoff's junction rule, and the Kirchhoff's junction rule states that the algebraic sum of the currents into any junction is zero. The algebraic sum of the currents into any junction is zero, and it can be written mathematically as summation I at junction is equal to 0. This law can also be written as the sum of all the currents directed towards a junction in a circuit is equal to the sum of all the currents directed away from that point. See here, this is a point and some currents are directed towards that point and some currents are directed away from that point. So here the currents I1, I2 are directed towards the point and currents I3, I4, I5 are directed away from that point. So these two are the incoming currents and these three are the outgoing currents. So if we consider the currents which are directed towards the junction as positive and the currents which are directed away from the junction as negative, and here it can be written as Kirchhoff's junction rule here can be written as I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. I have considered I1, I2 as positive and the remaining three currents I3, I4, I5 as negative because they are leaving from the junction. So the algebraic sum of the currents into any junction is 0. It means I1 plus I2 is equal to I3 plus I4 plus I5. That means the sum of the currents entering into the junction is equal to sum of the currents leaving from the junction. Okay? And the junction rule is based on conservation of electric charge. No charge can accumulate at a junction, so the total charge entering the junction per unit time must equal to charge leaving per unit time. Charge per unit time is current. So if we consider the currents entering to be positive and those leaving to be negative, the algebraic sum of currents into a junction must be 0. Okay? Now let us study the Kirchhoff's loop rule. The Kirchhoff's loop rule states that the algebraic sum of the potential differences across each element around any closed circuit loop must be 0. Here, element means it could be either a resistor or a battery. That is, this loop rule can be stated mathematically as summation delta V in a closed loop is equal to 0. Here delta V denotes potential difference between any element and this is the summation symbol. Okay. This law can also be written as the algebraic sum of the increases and decreases in potential difference across various components of the circuit in a closed circuit loop must be 0. And the loop rule is based on the conservation of energy. This result states that there is no net change in electric potential around a closed path. Kirchhoff's second rule applies only for circuits in which an electric potential is defined at each point. Okay, and the Kirchhoff's two rules are applicable only for DC currents. We need to follow some sign conventions in applying the loop rule. So what are those sign conventions? Let us see here. In applying the loop rule, we need sign conventions. The following are the sign conventions you see here. This is the first sign convention. EMF, that is electromotive force of the battery, is taken as a negative when we move from positive terminal to negative terminal across the battery. See here, this is a battery and whose EMF is E, and this one is the positive terminal and this one is the negative terminal, and here I am traversing the battery from left to right. That means I am moving from left to right. So when I move from left to right, the potential is decreasing. Hence we have to take the EMF of this battery as minus E. So here you can see here I have denoted these 2 points by H and L. H means higher potential and L means lower potential. So We know that the positive terminal of the battery is at higher potential, the negative terminal is at lower potential. Now I am moving from higher to lower. That means the potential is decreasing. So if we take the potential difference between the points A and B, delta V is equal to VB minus VA, because I am traversing from left to right from A to B. So the potential difference VB minus VA, we get minus E, that is negative. Next, second sign convention, you can see here, EMF of the battery is taken as positive when we move from negative terminal to positive terminal across the battery. Same battery here. Here is the direction of traversing. That means I am moving from point to B to point A. That is from negative terminal to positive terminal. I am crossing the battery. That means when I cross from negative to positive terminal, potential is increasing. Hence, we have to take the EMF as positive. So see here, A is at higher potential and B is at lower potential. Here I am traversing this battery from lower potential to higher potential, and here delta V is equal to VA minus VB, that is VA is greater than VB, hence we get plus E, that is the EMF of the battery should be taken as positive. Here simple thing is that when I traverse from lower potential to higher potential, that is while traversing an element, if the potential increases, we should take it as positive, and if the potential decreases, we should take it as negative. The potential difference should be taken as a negative. Okay. Next, the third convention is the potential difference across the resistor is taken as a negative when we move along the direction of the current through the resistor. See here, this is a resistor through which current is flowing from A to B. We know that current always flows from a point of higher potential to point of lower potential. So the point A is at higher potential, the point B is at lower potential, hence current is flowing from A to B. Okay. Here H denotes higher potential, L denotes lower potential. So the point A is at higher potential, the point B is at lower potential, and the potential difference across the resistor is IR. According to Ohm's law, V is equal to IR. The potential difference across the resistor is IR. When I current is flowing through the resistor R, some potential difference will be developed across the resistor, that is V is equal to IR. Now, if I traverse this element resistor from A to B, the potential is decreasing. See here, this is the direction of traversing. So if I move from A to B, it means that the potential is decreasing. Hence we have to take IR as minus, negative. So delta V is equal to VB minus VE, it is minus IR. Okay. And the fourth convention is opposite to this. The potential difference across the resistor is taken as positive when we move against the direction of the current through the resistor. You see here the same resistor. Here I am showing. So A is at higher potential and B is at lower potential, and the potential difference across the resistor is IR. And if I traverse this resistor from B to A, B is at lower potential and A is at higher potential. So while traversing from B to A, the potential is increasing. This is the direction of traversing. That means I am moving from point B to A. That is from lower potential to higher potential. For that reason, we have to take IR as positive. Delta V is equal to VA minus VB. We get plus IR because VA is greater than VB. Okay. So these are the sign conventions we must follow in applying the Kirchhoff's loop rule. Okay. Here is a note. It is advised to write H for higher potential and L for lower potential across all the batteries and resistances of the loop under consideration while using the loop law. Then write minus while moving from H to L and plus for L to H. That is, in moving a loop, if we cross an element from higher to lower potential, then take the potential difference across that element as a negative, and if we cross the element from lower potential to higher potential, then take the potential difference across that element as positive. Okay. Across a battery, write H on positive terminal and L on negative terminal. Across a resistance, keep in mind the fact that the current always flows from higher potential H to lower potential L. So here is an example. Okay, this is a circuit. Current is flowing like this clockwise direction in this loop. It is a closed loop. Okay, so current is flowing in clockwise direction like this. Now let us apply the loop law to the loop A, D, C, B. Before applying the loop law, let us write H and L across each element. See here, I will start from this battery. Here plus means this positive terminal is at higher potential, so write H, and this is negative terminal means at lower potential, write L, and here current is flowing from B to C towards right. So this point is at higher potential, this point is at lower potential, so write H here and L here. Similarly, H, L here, H, L. H means higher potential, L means lower potential. In a resistor, current flows from higher potential to lower potential. For that reason, here I have written H and here L. Now, let us apply the loop law. In the loop shown in figure, we have marked H and L across all batteries and resistances. Now let us apply the second law, that is loop law, in the loop ADCBA. So I will start from A to D and I traverse the loop from D to C, C to B, B to A like this. So I am applying the loop law to the loop A, D, C, B, A. Okay, see here. First, I will move from A to D. So here I have to cross this resistor, and I am moving from lower potential to higher potential. That is, I am traversing this element from lower to higher. So potential is increasing. Then you should take the potential difference across this resistor as plus. So I current is flowing through the resistor means the potential difference developed across this resistor is IR2. So take this IR2 as positive. The equation will be plus IR2. So I reach to the point D, then I have to move from D to C. Here there is a battery. So I am moving from L to H, lower potential to higher potential. Then take the EMF of this battery as plus E2. Now I am here at C. Then I am moving the resistor, that is I am crossing the resistor from lower to higher potential. That means potential is increasing. So you take the potential difference across the resistor R1 as plus IR1, and here battery L to H, lower to higher I am moving. So when the potential increases you should take positive, when potential decreases while crossing any element you take minus. So here the EMF of this battery E1 should also be taken as positive, plus E1 is equal to 0. The sum of all the potential differences across each element in a loop is equal to 0. Okay, the algebraic sum. Okay, now let us do some problems on Kirchhoff's second rule, that is loop rule. Example 1, write the loop equation for the potentials in the given circuit. Here is the circuit and the current is flowing like this. So here the potential difference between the two terminals of this battery has been given as V1. Now here is the solution. In A, B, C, D, A loop, that means I am traversing the loop like this: A, B, C, D, E, like this. Okay, see here. First I will move from A to B. So here it is at higher potential, it is at lower potential. That means I am moving from higher to lower. That is, I am crossing the battery from higher to lower. Potential is decreasing. So when potential decreases while crossing, take it as minus. So minus V1. Next, current is flowing towards left in this direction from C to A. I am moving from B to C, that is opposite to the direction of the current. So this point is at higher potential, this point is at lower potential, you see here. So I have moved from lower potential to higher potential, that is potential is increasing. Then take the potential difference across the resistor R1 as plus IR1, and from C to D no elements are there, D to E no elements are there, E to A no elements are there. So the algebraic sum of the potential differences across each element is 0. You see here, this is equal to 0. So when I applied the loop rule for the loop here A, B, C, D, E, A, I got this equation. Here is another example, example 2. Write the loop equation for the potentials in the given circuit. So this is a circuit. We have to write the loop equation to the loop A, B, C, D, E, A. Solution. Let us apply loop law to the given circuit from the A, B, C, D, E, A loop. A, B, C, D, E, A. That means I will traverse this loop like this. So first I will move from A to B, then B to C, C to D, D to E, E to A. Okay. See here, I am moving from A to B. So current is flowing towards left. That means this point is at higher potential, this point is at lower potential. We know that current always flows from a point of higher potential to the point of lower potential. So see here I have moved from L to H, lower potential to higher potential. Then we have to take the potential difference across the resistor R1 as plus. Why? Because the potential is increasing. While moving an element, while crossing an element, if the potential increases, take the potential difference across that element as positive. So here plus IR1. Next, I will move from B to C. Current is flowing like this. Okay, so I am moving opposite to the direction of the current. That means here it is lower potential, here it is higher potential. See here. So I have moved from lower to higher potential. That is, potential has increased here. For that reason, I will take the potential difference across the resistor R2 as plus IR2. Then I will move from C to D. So here positive to negative. See here, higher to lower. So I have moved from higher to lower. That means potential has decreased. Then we should take the potential difference across the two terminals as minus V1. Next, I will move from D to E. That is opposite to the direction of the current through the resistor. Current is flowing like this. I am traversing this element from right to left. So here is higher potential, here is lower potential. That means H to L. So I have moved from L to H. Potential increases. So take the potential difference across this resistor as plus IR3. Next, plus to minus E to A. So H to L, I have moved from H to L, higher to lower. So potential decreases. So take the potential difference across the terminals of this battery as minus V2. So this is equal to 0. That means the algebraic sum of all the potential differences across each element is 0. While taking the potential differences across each element, we have to follow the sign conventions. Okay, so I will show you some more problems on Kirchhoff laws in the next upcoming videos. Okay, thank you.